Hi there. So I'm redoing a lecture because I made a mistake on one of the formulas, and I just wanted to correct it. Um, so what we're going to be talking about today is more work energy examples, looking at rigid bodies particularly, because I think, uh, especially at this section of the course, it's kind of fun because it's no longer depends on vectors; it's all scalar. Uh, Identify how to recognize these problems and start looking at standard approaches that work to make this kind of sensible. Um, so if you continue, so I have a 25 kilogram bar that's rotating downward at 2 rads per second. The spring has an unstretched length of 0.45 meters and a spring constant of 180 newtons per meter. At what angle, measured from the horizontal, does the bar rotate before it stops? Now I have a funny system here, and I should sort of point that out. So I have over here a cylinder or disc that allows this to remain horizontal throughout the all time. So the spring is going to move, in this case it'll move to the left as the bar drops. So omega is 2 rads per second, distances are 1.2 meters and 2 meters in this particular case. It's a force, velocity, and distance problem, and conservative forces and distance leads to the use of conservation of energy. So first, let's calculate the total energy. So what we do is you don't have to worry so much, and I see a lot of people who are doing these problems tend to use work. You shouldn't use work. You should use potential energy where you can. So for example, I'm going to define a datum. It's that upside down triangle with the lines in it. I also have very properly done my axes, in this case, X, Y, and I'm going to have a positive clockwise moment because I'm just doing this as a scalar calculation. It is not a vector calculation, and so this is not going to cause me an error as long as I draw out everything that I'm looking at. Easier coordinate system for that problem. That's the only reason, because the bar is swinging in the clockwise direction. I know that. I mean, as soon as I release this system, it'll go. So its next position is going to be somewhere down below, so distance theta. And I can say, well, first of all, when it starts, T1 equals 1/2 I naught omega squared. And there's no translational velocity because it's sort of attached to that bar or pin. And so everything is with respect to I naught. Now, I naught is equal to 1/3 m rod L squared. And at this point, you should be very comfortable with this. You've already done multiple cases, and you've looked at cases like this. So you know what to expect from a bar that's pinned at a point. And if it's pinned at a point, it'll go to 1/3. Make sure that you know how to do this, and make sure you know what the definition is. The initial kinetic or potential energy is going to be associated with the spring potential, which is 1/2 K, the length 1, which is defined on that figure, minus the unstretched length. On the other hand, you have T2 where it comes to a stop, and you have V2, which is going to combine gravitational potential and spring potential. So you have minus mg L rod over 2 sine theta, so it's halfway because it's the g of the rod that determines where the gravitational potential is defined, and then 1/2 K length 1 plus length rod sine theta minus length unstretched squared. So I'm just trying to cheat a little bit. I know where the triangle starts, and I just want to sort of cover the last little bit, which is associated with the rod and the angle. So that's all I'm doing here. So if I do that and substitute in all the terms, I'll get two results, either minus 27.78 degrees, and since I've defined negative as counterclockwise, that would mean the rod has gone up, or 23.4 degrees. Again, this is one of those cases where I'm solving a problem and I have to use the physics to explain what the final answer is. But you should be comfortable with it. You can do it a number of different ways. You can do this with SMath. You can calculate this. This is not that bad. You'll have x squared. You substitute as sine theta for x squared. Okay. Theta equals 23.4 degrees. So next one. 15 kilogram pulley A has a radius of gyration KB equals 1.16 meters. Again, this is going to be one of those cases where you should be very familiar with what's happening with pulleys and radius of gyration. You'll see lots of radii of gyration when dealing with pulleys. Determine the speed of the 8.5 kilogram crate C at the instant S equals 0.25 meters. S is defined there. Initially, the crate is released from rest when S equals 0.1 meter. The pulley at P rolls downward on the cord without slipping. Neglect the mass of the pulley and the cord as it unwinds from the inner and outer hubs of pulley A. So I gave you the answer. I have, first of all, on the left-hand side, it's all gravitational potential. On the right-hand side, I have spring potential plus kinetic energy minus the gravitational potential as it drops still further in this case. The velocity of C is just going to be the average, RA plus RB divided by 2 of omega, and RA is the inner and outer, RA and RB are the inner and outer radii, respectively. So if I substitute in the terms, I get 19.7 rads per second, or a final velocity of point C of 3.45 meters per second. Look at the velocity directions. And as much as possible, when I'm doing examples like this, there's not much to say about them other than to tell you here's the answer, because these are scalar relationships. I just need to know point 1 to point 2. I don't like using work, and I don't like using work because every time I use work, I need to think about directions and things that are happening. Gravitational potential, spring potential, all I'm thinking about is position 1, position 2. And I'm hoping that this convinces you not to use work as your mechanism of solving these problems. Finally, you're pulling on a rope with a force of 500 newtons. The attached 120 kilogram spool, K of the spool is 215 millimeters, starts from rest. Determine its angular velocity after O has moved 1.5 meters. O is the center. Determine that the spool rolls without slipping. You'll see a lot of rolling without slipping or slip. Get used to them. And there's other videos where I talk about this, and there's also sort of a summary video on the kinetics of rigid bodies, looking at sort of standard points of instantaneous centers. And as much as possible, it isn't enough in this course to do these examples. You really have to understand what the definitions are and where they're coming from. Once you do that, the examples should make more sense. It's hard to follow sometimes without knowing why we're making these statements. 300 millimeters, 150 millimeters for the two radii. What's happening with the spool? I've got O to the center, and I've got P, which is the outer side. You know this already, but remember, rolling is occurring at the point of contact with the wheel. Okay, so there it is, RP with respect to the instantaneous center, RO with respect to the instantaneous center. So then, what next? If I look at an instantaneous center, I can draw a triangle out, omega R or alpha R, depending on what I'm interested in. Omega R in this case is V, and in that case, I can just calculate everything. Now, the interesting thing also is that clearly the velocity of point O is less than the velocity of point P, the translational velocity. The angular velocity, however, is exactly the same in both cases. V at O is equal to omega RO with respect to IC, and IO is equal to mk naught squared, which is the radius of gyration you were given at the beginning of the problem. What's happening with the spool? You know this already. Okay, so continuing. So you put in your T's, 1/2 mv naught squared plus 1/2 I naught omega squared. T is equal to 8.17 omega squared. What about the forces? What's doing work? Okay, so I've got force normal. I've got mg, which is acting normal to the direction of motion, and I also have this friction force. And friction force often causes trouble. Forces in green don't do work, and the important thing here is that force of friction cannot displace. If it cannot displace, it cannot move. If it cannot move, it cannot do work. So the only thing doing work in this case is going to be point P. Now, point P is going faster than point O, which means that for the same distance O, P is actually going to displace a larger distance. And it goes, for the 1.5 meters that O goes, P is traveling a distance of 2.5 meters. If you want to look at some fun results on what this means, look at rear differentials. And there's a really cool video from the 1930s explaining them. What about forces? Okay, continuing. Work done by the cord is positive because as its pull is occurring, it's going in the same direction. So work is equal to force P SP. Now this is one of the few cases where work is actually worthwhile because work is really easy to define. It's in the direction of motion. I don't have to think very hard and I get 1125 joules. So what about rotational speed? So the last thing is everything's there. I have T1 0 because everything starts from rest. I have the work done, 1125 joules, and I have the final result of 8.1735 omega squared. I've neglected gravitational potential because the center of mass, has traveled in a horizontal path, and there's nothing that's going to occur in terms of change of potential. So I don't even have to calculate it. If I did work, I probably would have to say position 1, position 2, subtract the 2, and say, okay, 0. Omega is equal to 11.7 rads per second. Super. Great. And from there, really, it's just looking at two types of problems. Rolling requires you to think about displacement carefully. Organize your thoughts before solving. Thank you very much, and we'll talk again later.